What is Monte Carlo simulation? How does it work? Let's look at an example of the Monte Carlo method. Here we have a circle inside of a square. Of course, we know how to find the area of these two shapes, but let's do it using a Monte Carlo simulation. Let's say d, our diameter, or the length of one side of our square, is 4. This makes the area of our square 16 and the area of our circle a little over 12.5. However, to find the area of the circle, let's put 10 random dots within the square and count how many out of the 10 are inside of the circle. This gives us a ratio of the circle to square, which gives us a circle area estimation of 12.8. Not bad, but when we increase the number of samples from 10 to 10,000, things will improve noticeably. Our ratio gives us an estimated area of 12.616, less than 1/20th off of the actual area. This might seem very useless, as we can easily calculate the area of a circle. However, you can likely see how this comes into play when finding the area of a more organic, less equationally consistent shape. In short, we defined a random process, picking a point inside of the square, and used repeated sampling of that random process to estimate some quantity that we wanted to find. This brings us to our big example, using Monte Carlo simulation for geometric Brownian motion. First, we'll write our equation and define these variables. Just so we're all on the same page, S sub t, mu, and sigma are our quote-unquote deterministic values, whereas the random process that we are using is W sub t, or Brownian motion. Typically, Black-Scholes utilizes geometric Brownian motion, but since we aren't working with actual values, the difference is not super necessary for a basic explanation. Starting at S sub 0, we simulate this random process a few times. Worth noting is that I am using a volatility value of 1/5, or 0.2. A couple fun lines, sure, but the magic really comes in when you repeat this process tons of times. Here we have 100 simulated paths. Now we can easily see a range where we might expect our stock price to fall in the future, giving us much more accurate pricing estimates. I noted that we are using a sigma of 0.2. What do you think will happen if we double our volatility? Well, as you might guess, this leads our estimated paths to stray up and down much further than before, reaching significantly higher highs and some lower lows. From there, we average the final prices, finding our expected value, and a bunch of other statistics that might be useful to you when trading. Now, a couple of key points. First, these visuals use geometric Brownian motion, most commonly used for asset pricing models. In short, GBM builds on standard Brownian motion by introducing drift. Secondly, when using Monte Carlo simulations, first know that risk-neutral pricing is usually assumed. Various traders and analysts have their own opinion on this. Lastly, the law of large numbers means that with more simulations, we are likely to get closer and closer to the actual underlying distribution. There's a lot to say on each of these points, so study on your own as well to understand them to the best of your ability.